The volume of an ideal gas is 5.0 times 10 to the power of negative 2 meter cube. The pressure is 3 atms and the temperature is 200 Kelvin. The gas is first heated at constant volumes to twice its original pressure. The volume is then expanded isothermally to its original pressure. Lastly, by keeping its pressure and temperature constant, the gas is isobarically returned to the original volume by letting gas escape. A. Sketch a PV diagram for the entire thermodynamic processes undergone by the gas. Label the diagram clearly and completely. B. Compute final numbers of mole of gas. Three thermodynamic processes mentioned in the questions. The first one is the constant volume. That means it is the isochoric process. The second is the expanded isothermally, means that this is the isothermal process. And the third one is the isobarical process. To sketch the PV diagram, now we label the x-axis as the V in the units of 10 to the power of negative 3 meter cubes. And for the vertical axis, we label it as a P, pressure in the atm. The initial state of the ideal gas is given in the questions, where the volume is 5.0 times 10 to the power of negative 2 meter cubes and the pressure is 3 atms. So now we use a dot to represent the initial state and labels the pressure as 3 atm and the volume is 50 times 10 to the power of negative 3 meter cubes. So we need to do some conversions adjustment for the value label, because in the question it is 5.0 times 10 to the power of negative 2, but this one is 50 times 10 to the power of negative 3. Actually, they are the same. First process, the gas is heated at constant volume to twice its original pressure. This is the isochoric process, so we have a vertical line. The arrowhead is pointing upwards because the pressure is changed from 3 atm to 6 atm. The volume is constant, which is fixed at 50 times 10 to the power of negative 3 meter cubes. So when this gas is increased in temperature at the constant volumes, when the pressure changes from 3 atm to 6 atm, the temperature will increase. That's why it says that the gas is heated. In the second process, the gas now is undergoes the isothermal expansions, and the pressure is reduced to original pressure. So for isothermal process, we have a curve in the PV diagram, and since the pressure is reduced back to its original pressure, so we know that the curve, when we draw it, we have to stop it at the level which is the same as the original state. That means it is 3 atms. Last process, it is isobaric. Isobaric means the pressure is constant. But this process is a little bit special, because now in this process, the gas is allowed to be removed or escape from the system. And by doing that, it is possible to keep the pressure and the temperature constant. But basically, the gas is considered as isobaric. So that's why we will have a horizontal line which is points to the left. So that means now the gas will maintain at the pressure 3 atm, and it will return to the original volume. So that means it will be equal to 50 times 10 to the power of negative 3 meter cubes. If we label the states for the gas, we will have state number 1, state number 2, state number 3, and state number 4. For the same points on this PV diagram, this one, please take note that the states of the gas is not the same. Although they have the same pressure and the same volume, The reason is because in the last thermodynamic process, which is isobaric, in this process, some of the molecules is allowed to escape from the system. So that means when it is in the state number 1, the number of mole is not the same as the number of mole in the state number 4. So that is why, although it is represented by one point in the PV diagram, we consider them as two different states. That means the pressure P1 is the same as the P4, which is 3 atm. V1 and V4 are the same, which is 50 times 10 to the power of negative 3 meter cube. But the number of mole for the 1 and 4, state 1 and state 4, they are not the same, simply because in the process of this isobarics, there are some gas is removed from the system. And also from the information given by the questions, we know that in the process from state 3 to state 4, the temperature is kept constant. And we know that in isothermal process, temperature of the state 2 and the state 3 are the same. So that means the temperature for T2, T3, and T4, they are the same. But the T1 and T4, they are not the same. That's why we say that the state for 1 and state 4, they are not the same state. In this case, although they are represented by the same point in the PV diagram. Previously, the questions that we discussed, especially for the cyclic process, when the state come back to the original point in the PV diagram, we consider them as the same because the number of mole are kept constant. But now in this case, it is a difference because the sum of the gas is allowed to remove from the system. So we have the state 1 and state 4 not the same, even though it is at the same point in the PV diagram. This is a key for these questions that you need to take notes. By drawing, we can represent the state number 1 as the system, something like this. And the state number 4 is like this, where the difference between them is that although they have the same pressure, these two gases, these two systems, they have the same pressure, they have the same volumes, but the number of mole is different. And the temperature between them is also different. Now we can start to compute the final number of mole of the gas. So that means you want to find the N4, not the N1. Before we consider the state number 4 and we write down the equations of state or ideal gas law for the state number 4. So we have P4V4 equal to N4RT4. We change the N4 as a subject of these equations. The pressure P4 is the same as the P1, which is 3 atm, and V4 and V1 also the same, which is 50 times 10 to the power of negative 3 meter cubes. And for the temperature T4, it is not the same as the T1. From the questions, we know that the process from state 3 to state 4, the temperature is kept constant. So that means T4 is the same as T3. And T3 is the same as T2 because from 2 to 3, this is the isothermal process. So that means T4 is the same as a T3 and T3 is the same as T2. So now we substitute the T4 by the T2. We know the value of the P1 and V1 from the PV diagram. So that means to find out what is the N4, we need to know what is the T2. To find the temperature T2, now we consider the isochoric process from state 1 to state 2. Since this is isochoric process with the volume constant, then we can write now P1 over T1 equal to P2 over T2. Bear in mind that this is in the process from 1 to 2, the number of mole of the gas is the same. So that means M1 is equal to the M2. Our aims is to find the temperature T2. So now we change the T2 as a subject and to get the T1 multiplied with the ratio of P2 over P1. P2 is twice of the P1, where the P2 is 6 atm and the P1 is 3 atms. Therefore, we can simplify this to the T2 equal to 2T1. Substitute the T2 equal to 2T1 into the equations number 1 here. Then we have N4 equal to P1 V1 over 2RT1. But the P1 V1 over RT1, in fact, it is equal to the N1. So that means N4 is half of the N1. Now we start to substitute the value. For the P1, it is 3 atm. So please remember to change it into Pascal by multiplying with 1.01 times 10 to the power 5 Pascal. V1 is the 50 times 10 to the power of 3 meter cube. R is a gas constant 8.31, and the T1, this T1 is given by the equations in the equations, which is equal to 200 K. Finally, we obtain N4 equal to 4.56 mole. Now again, from these equations, we know that N4 is half of the N1. So if you want to know what is the value of the N1, you can simply, by taking the 4.56 mole multiplied by 2, you get the value for the N1. So N1 and N4 not the same. This is a key message that you need to take notes to solving these equations. From the process of 1 to 2, the N is the same. From 2 to 3, N is the same. But from 3 to 4, since there are some gases escape from the system, so the number of mole will change due to this process. So N1 and N4, they are not the same.